So I think we should get started. So this class, we're mainly going to go through a review session on all the contents that we have learned, and also get prepared for the midterm exam. So until now, we have been mainly talking about some introduction contents on the air pollutants, and we spent most of the time talking about particulate matter, right? And this is actually I mean, the contents that we have learned will be covered in the midterm exam. So we're not going to include some other things in there. So, and also the problems will be quite similar to the homework problems. So I would say the best way to get prepared for the exam is to maybe redo your homework problems, get familiarized with the process. So during the exam, you don't need to go through the textbook and then go through line by line, right? And actually, before we talk about the review session, there's one final last piece that we haven't talked about yet. So we have introduced quite many particulate matter control devices, and there's one final device that we haven't talked about. It is called the particulate scrubber, or the particle scrubber. So I would say the particulate scrubber is kind of like a combination of the existing PM control devices. So typically these particle scrubber will be made of these large cylinders. And in the large cylinder, the air can flow in different patterns, but at the same time, we're going to spray water downstream it. So basically what happens is we're going to introduce dirty air in here, and then the water droplet will fall down. And then because the water droplets are typically larger, right, it's going to collide with the smaller particles and then attach them and then basically clean them up, right? And then because of the higher gravity of the water droplets, it's just going to settle down. So I would say it's a combination mechanism of the gravitational settling and cyclone. Okay, the cyclone uses inertia, right? For example, this type of scrubber here. So we're introducing the air in this rotation or swirl pattern, right? And then the larger particles will just get removed from the stream, right? They have a higher inertia. And then at the same time, we spray water droplets to the wall. So in this way, the particle basically will become larger, right? Due to the water colliding with the particle. And because of the larger size, they're going to have a higher inertia. So we can more efficiently remove these particles. But still, the particle scrubber has the problem of low efficiency for very small particles. So because it's still utilizing the settling and the cyclone, right? We know that these two are not very efficient for very small particles. So to remove those very small particles, we still need to refer to the ESP or the backhouse filter, right? And in terms of the efficiency of this particle scrubber, there's a set of equations that we can use. So basically, if we want to calculate the efficiency of the device, we need to first know what is the penetration, right? So the penetration is basically 1 minus the efficiency. So this is a fractional particle that can exit through the particle scrubber. And that follows the equation of exponential minus AD BT e to d divided by QG. Okay, so it is a quite complicated equation here. So, but if you think about the mechanism for removing these particles, these parameters actually make sense. So let's say first AD here, let me just label this out. So AD here is the cross-section area of all droplets. So what this means is that if you consider the water droplets being straight down, and then if we just take a cross section, so what is the area of all the droplets in there, right? And then let's think of two extremes. So let's say if there's no water. So if there's no water, then that basically means that AD is equal to 0, right? If AD is equal to 0, then if you plug that in, this term equals to 1, which means that all of the particles will penetrate through this particle scrubber, right? And let's say if AD goes to infinity. So it might be too extreme here. So basically, if the AD is infinity, then this is just like a faucet, right? So we're just flushing water through. So no particles will penetrate. Right? If no particle penetrate, then basically this penetration should be 0. Right? That works for here too, because AD goes to infinity, this whole term goes to negative infinity, which is equal to 0. And then the efficiency will be 100%. Right? So this term makes sense. And then VT here is the terminal settling velocity of droplets. Okay. So also, let's say if the settling velocity of the droplet is very low, then that basically means that it's going to take a very long time for the droplet to settle down to the bottom, right? And also, typically, if the water droplet has a lower settling velocity, it means that the size is smaller. So actually, we're introducing more PM into the system, which is more difficult to remove. That's why the VT will affect the system. And then this eta D here is the efficiency of a single droplet in particle removal. So we need to consider the detailed physics in this particle removing process, right? So basically, because finally it's just the interaction between a single droplet and some tiny particles surrounding it. So we had to somehow calculate this, this single efficiency here and plug that into the system. So let's say if this single droplet is very efficient, then that means the penetration will become lower. If this single droplet is not efficient at all, then this eta D will become 0, and then the penetration will be 100%, right? So this factor also affects the efficiency. And finally, the QG is the total flow rate of water. It's a total flow rate of gas. It has the G here, the total flow rate of gas. So similarly, let's say if the flow rate of gas is very high, then it means that this process will become less efficient, right? Let's say QG become higher, and this whole term, this fraction becomes lower, and then because it has a negative sign, right? This whole term in the exponential become higher, right? So basically, it means that if the QG becomes higher, the penetration becomes higher, the system becomes less efficient, right? So basically, all of these parameters make sense in this equation here, and this is kinds of like a equation that's based on the experiences of engineering operation. Okay. So here I also have a short video about the particle scrubber. Go through that.
A packed bed scrubber, also called packed tower scrubber, is designed to remove both particulate matter . A packed bed scrubber, also called packed tower scrubber, is designed to remove both particulate matter as well as gaseous pollutants. The contaminated gas stream is fed into the tower. Inside the tower is a bed of special packing material. Nozzles spray scrubbing liquid on top of the packing material, and the liquid works its way down the tower. As the gas passes up through the packing material, the particulate and gas molecules come in contact with the film of scrubbing liquid on the packing. The contaminated liquid drains down through the packing material, past a packing support, and out through the bottom of the tower. The gas stream flows out through the top of the packing material, past the nozzles, and through a mist eliminator before exiting the tower.
Okay, so this is one type of the scrubber. So the scrubber means basically the cleaner, because scrub means clean something up, right? So scrubber means cleaner. So the advantage for the scrubber is that it's not only cleaning the particles. The design of the scrubber is mainly targeted at the gaseous pollutants, for example, the sulfur dioxide, nitrogen dioxide. So while it can absorb or remove those gaseous pollutants, it can also remove these particles here. So that's why we also want to introduce this particle scrubber in the PM removal devices. So we will learn more about the scrubber system when we talk about the control of the sulfur dioxide, because we know that coal-fired power plant, they just generate millions of tons of sulfur dioxide every year, right? So we have to come up with a system to remove those gaseous sulfur dioxide. And the system that we use is actually the scrubber, right? So this is the final PM removal device that we want to learn about. There's not a lot of design problems associated with this system. So finally, we need to talk about the cost of the PM removal device. So if you read the textbook, you will see that in the textbook for each chapter, when it talks about certain PM removal device, at the end, it also describes the cost, right? So the cost will include both the capital cost or capital investment, which is the cost for constructing this PM removal device. And also you have the operation or the operating cost. So the operating cost, for example, the ESP, electrostatic precipitator, we need to connect it to certain high voltage, right? So it's going to use some power. And also for
may you please share your screen, please?
Oh yeah, that's right. Let's see. Yeah, thanks. I just realized this. Right. I just wrote 2 lines here. Right. Maybe we can start up. So we haven't discussed the cost of the PM removal devices yet. So as I have introduced, the cost will mainly include the capital cost, which is for constructing the system, and also the operating cost. As we have introduced the ESP and backhouse filter, so they're going to require pretty high operating cost, right? Because we need to connect it to a certain high voltage power supply. And also for the backhouse, we need to replace the bags quite often. We need to shut off the compartment off for some time and then connect it back online. So these systems are going to cost quite a lot of operating cost. But for the, for example, for the cyclones, so what we mentioned is that Cyclone is basically just a metal case, right? So once it's set up there, it doesn't need a lot of maintenance. We're just passing through the flue gas through the system. So there are definitely some differences for each type of the PM removal device. And in your team project, you're going to go through the details on the cost analysis, right? So what is the cost for building up such a PM removal device? Right? And for this class, we're just going to talk about very basics in this cost analysis. So typically, the cost of these PM removal device, let's say we're going to use the equation P equal to A x to the power of B plus C, okay? So the X here, is related to the operating parameter of the device. So for example, if we're talking about the cyclone, right? So the X will be the cyclone inlet area. Okay, so it might sound quite arbitrary here, but this is what people find out basically by building different types of these cyclones. What they find out is that actually the cost associated with the cyclone can somehow scale with the inlet area of the cyclone. So because the inlet area determines the geometry, right? And we mentioned that for the cyclones, it has a set of geometry, let's say the LAPO type, right? Once you know the diameter, you should be able to calculate all the different dimensions. So this X here is related to the inlet area of the system. Yeah, see someone still in the waiting room. Probably has been there for quite a long time. So, and for the ESP, the X is related to the plate area, or this total plate area. Okay, this kind of makes sense because the cost of the ESP is mainly, I would say, largely determined by how many plates we're going to use, right? So that's related to the total plate area here. And for the backhouse, this X is related to the cloth area. And finally, for the scrubber, this X is related to the gas flow rate. So in general, we want to simplify this cost calculation so that we can basically just refer to one type of the operating parameter, and then to calculate this total price or total cost here. Okay, so I would say that maybe you guys can spend more time in your team project to go through those final sections in each chapter about the cost, so that you can get a more accurate estimation of the cost for your devices. Okay, so these are the last pieces of the PM, and I think now it's probably a good time to go through the contents again, and then to get prepared for the midterm exam. Okay. So if we recall, if we look back on all the contents that we have learned, so basically it's these points here. Okay, so these will be covered in the exam, which are first the criteria of air pollutants, and also what are the first is the criteria air pollutants, which are the most important types of air pollutants, right? So we have been mainly dealing with the PM, right? And then we know that there are sulfur dioxide, nitrogen dioxide, CO, lead, and ozone, right? We further divide them into primary air pollutants, secondary air pollutants, based on how they're being formed. So we also introduced something on the air quality, right? The air quality index. How do we calculate that based on the concentrations of these air pollutants? And there was a quite important section on the in the introduction side. So until now, we haven't talked about too much of it in the PM analysis. But later on, when we talk about the gaseous air pollutants, we're going to use this unit conversion quite often. Okay. So the unit conversion is basically using the ideal gas law to convert the quantities from all different types of units. Okay. For example, it can be mole fraction. You know that mole fraction can be can have the units of percent, right? ppb, ppm, ppm, so on. Right. Mass concentration is going to just be the mass of this single species divided by the total volume. So those can carry the unit of, let's say, kilogram per meter cube or milligram per meter cube, so on, right? And then we also have the number concentration. This is just the mole per meter cube or number of molecules per meter cube. So what we're trying to achieve is basically converting from one another, right? I think in your homework homework problems, you deal with quite many of these practice already. So here, I just want to demonstrate this process again, so that if there's anything unclear for some of you, you can try to understand how are we going to deal with this problem. Okay, so here I will show an example problem, and this is also one of your homework problem. So this is 1.25, and if you can find your previous homework, you can. I think now is also a good time you find it out, right? So let's just spend maybe 1 minute to read through this question and try to understand what it's asking us to do. Okay. So basically, it involves the nitrogen dioxide system, and we want to convert the unit from one to the other. So, okay, I'll just read this problem now, if you haven't gone through that. So assume that the nitrogen dioxide concentration in a house with a gas stove is 150 microgram per meter cube. It wants us to calculate what is the equivalent concentration in ppm. Okay, so just based on this problem, we know that it's actually trying to let us convert the mass concentration into mole fraction, right? Right, so this A here means this single species, and we're talking about nitrogen dioxide here, right? So we already have its mass concentration. We want to derive its mole fraction. So as we have introduced here, we need to convert one from another in terms of the units, right? So how do we do that? I think during our classes, I already gave those conversion from one to the other. I think if you have the class notes, you can still find it. But here, I'll just try to derive it again. Okay, so we're trying to convert basically from Na to N, Na divided by N, Na divided by V, and Ma divided by V. Okay, so for these two, it is quite straightforward. Mainly because, let's say, if we build up an equation here, then we know that Na is equal to Ma divided by the molecular weight of A, right? So we can get Ma divided by V multiplied by 1 over molecular weight of A. So in this way, we can convert from the number concentration into the mass concentration, okay? And then how do we convert from here to here? So we're going to use the ideal gas law, which is PV equal to nRT, right? We have N equal to basically PV divided by RT. So once we have this relationship, we can plug in this N here. So we have Na divided by V, or Na divided by PV, multiplied by RT, right? So what we did is just plugging in the N into this location here, right? So we have Na divided by V multiplied by RT divided by P. So with this relationship, with this derivation, we can convert the mole fraction into number concentration, right? And further, we have number concentration into the mass concentration. We further plug that in, Ma divided by V multiplied by RT divided by P multiplied by the molecular weight of A. Okay. So basically, we're plugging in this term here into here. Right? Any questions? Good. So basically, now we have the equation which converts from the mole fraction into mass concentration, right? And then this problem wants us to calculate the mole fraction in ppm. So it is quite straightforward. We know that the Na divided by N is going to be equal to Ma divided by V. We know that is 150 microgram per meter cube multiplied by RT. So RT is 8.314 joule per mole per K. And then as standard STP means 273.15 Kelvin, and the pressure is 10 to the 5th Pascal. Okay, so here we can just plug in this number of 273.15 K divided by 10 to the 5th Pascal, multiply them by the molecular weight. So for the nitrogen dioxide, the molecular weight is basically 14 plus 2 multiplied by 16, right? And that is 46 gram per mole. 46 gram per mole. And actually, I think most of you have got to this step here, okay? So I know that there are very few of you who were using the equation in the textbook. So I would say that
Doctor,
the equation, yes?
excuse me.
Yes.
You mentioned STB, that's mean the temperature 25 Celsius and the pressure 1 atom, right?
So it really depends on which STP we're talking about, right? I saw that there are 2 types of STP.
Okay. If I use this, it's correct? 25 Celsius the temperature and the pressure 1 atom, it's okay?
That's also fine. I would say that this problem is probably not stated well. Yeah, so
solve this problem. Yeah, okay.
Yeah, this is I mean, also at this temperature and pressure, you'll find out that it's not going to affect the final answer by a lot.
Okay, thank you.
Yeah, so in the future for these problems, we'll just state clearly what is the temperature, what is the pressure. All right, any other questions? Good, okay, so we're mentioning that there are maybe 1 or 2 of you who are using the equation in the textbook. So the equation in the textbook, I would say it's a simplified version, but it's also having a lot of assumptions regarding temperature and pressure. I would say, I would urge you to use this equation, okay? So to use this type of relationship so that you can plug in the values more clearly in there, because there's no assumption here, except that we assume the gas will follow the ideal gas law, right? So basically, if you get to this step, then one important thing that you need to bear in mind is we need to use a standard unit, okay? So you need to unify all the units into the same setting. For example, the microgram per meter cube, this is not standard units. We know that for the mass, the unit should be kilogram, right? Similarly, in here, we shouldn't use gram, we should use kilogram here, right? So because of that, we need to further do some unit conversion in terms of the detailed mass values. So this will be 150 microgram per meter cube. So I saw that some of you prefer to use the method of just stating what is the relationship between different mass units. For example, we know that 1 kilogram is 10 to the 9th of the microgram, right? So in this way, you can cancel the microgram here, right? And then in this fraction here, you have 8.314 still joule per mole per K, and then 273.15, 10 to the 5th Pascal. And then for the molecular weight, that's going to be 46 multiplied by 10 to the -3 kilogram per mole. Okay, so now everything is in the standard units. We just need to use a calculator to type in the values to find out. So the answer for this equation here is 7.4 multiplied by 10 to the -8. Okay, and we want to convert it into ppm, right? You know that ppm, we need to multiply that by 10 to the 6th, okay? Because it's parts per million. 1 million is 10 to the 6th. So that's going to be 0.074 ppm. Okay, so I would say there are two things that we need to pay attention here. So the first thing is to use this standard conversion equation here. Okay, use the correct equation. Okay, and second thing is to use the standard units. So if you can make sure that you're using the correct equation and also standard units, I would say that you should be able to get the correct answer. Okay, try to practice more with this problem because I often see that in the exam there are some maybe quite a few of you that don't have any clue regarding this unit conversion problem, because this is quite important topic, especially for the second half of the semester, right? So we want to make sure that you can understand why are we going through a certain equations to calculate this unit conversion problem, right? So this is, I would say, a straightforward unit conversion, and there's also a problem that is not that straightforward, which is this problem here. It is quite, I'm quite happy to see that for this problem, quite many of you get the correct answer. I would have to say that this problem is not stated very well. You have to basically use your imagination to think about what is the drying process. So let's again spend maybe 1 or 2 minutes to read through this problem, okay? Okay, so let's get started here with this problem. So this problem is talking about the drying process of certain textile, right? So if you think about your dryer, so after we wash our clothes, we're going to store them in the dryer, right? And then it's going to flush dry air through the fabrics, through our clothes. And then the dry air will become wet, mainly because the solvent or the water in our clothes are getting picked up from the drying process, right? So if you read this problem, let's say a textile finishing process involves the drying of a fabric that has been treated with a volatile solvent. So this volatile solvents can be some organics, right? Because during the finishing of this textile, we want to maybe coat this cloth with some organics, right? So it has a property that degrades less frequently, right? So it can last for a longer time. So this drying process tries to remove this extra volatile content, okay? So originally when we put them in, there will be wet fabric. The wet fabric enters the dryer, but the wet fabric also contains 45% of the solvent. So if we think about, let's say this is our fabric, okay, then we know that 45% of the mass are actually the solvent, right? And then we're throwing that in to a dryer. Okay. So the wet fabric entering the dryer contains 45% of the solvent, and the dried fabric contains 3% of the entering solvent. Okay. So you can see that this 3% is not the final solvent concentration, but it's the 3% of the entering solvent. Okay. So if we set up a relationship regarding the properties of all the mass, let's assume that the original fabric mass is M. Okay, I also saw some of you just use 100, let's say 100 kilogram or 100 grams. That is fine as well, because finally these numbers will cancel out. But right now, if we use a more general form, let's assume that the mass of the fabric is M. So we know that, let's say, this is wet, this is dry, right? If we put in the total mass, solvent mass, and fabric mass. So the total mass, let's assume it's M. Then for the wet fabric, we know that the solvent mass will be 0.45 of M, right? Because it occupies 45% of the total mass. So because of that, we know that the fabric mass will just be 1 minus 0.45 of M, right? Because other than the solvent, it's just the dry fabric, right? So this is the fabric mass. And we know that for the dried fabric, it contains 3% of the original entering solvent. So we know that for the dry fabric, the solvent mass will be 0.45 M multiplied by 0.03, right? So this is what the problem stated, contains 3% of the entering solvent, right? And then the solvent-free air, which is the dry air going through this dryer, the air enters the dryer at a rate of 8 pounds per pound of solvent-free fabric, okay? So what that means is for every 1 kilogram, let's say every 1 pound of the dry fabric, is referred to this area. So let's use another color here. So for every 1 pound of these dried fabric, we have 8 pounds of the dry air, right? So what that means is we know already that this dry fabric is 0.55 M. So the amount of air that enters the dryer will be 0.55 multiplied by 8 of M, right? So this is how we can calculate the mass of the air entering the system, okay? So we know that finally when the fabric come out, this we call it dry fabric, but still it contains some quantity of the solvent. And then we have the wet air coming out, which is basically these solvents are being picked up by the dry air from the system, right? So now let's see what this question asks us about. So it first wants us to calculate the percentage of the solvent in the dried fabric by weight, okay? So basically it wants us to calculate, let's say this is a dry fabric, it's still dried out, okay? So now we know that after drying, the fraction of the solvent will be very less. And then most of it will just be the dry fabric, right? So we just need to know what is the fraction, the mass fraction of these solvent. So we have already shown here in this table here that the solvent mass in the dry fabrics is 3% of the 0.5 M, right? But at the same time, the fabric mass will not change at all. It's not like after drying, the fabric also lose some contents there. So the fabric is still in its original mass. So we know that this is still going to be 0.55 of m. Okay, so based on these two, we can calculate what is total mass. That's 0.55 plus 0.45 multiplied by 0.03 of m. Okay, so to calculate what is the percentage of the solvent in the dried fabric, then we can just divide this solvent mass by the total mass, right? So for this A here, we just need to plug in 0.45 m multiplied by 0.03 divided by 0.55 m plus, say, if we take the m outside, 0.55 plus 0.45 multiplied by 0.03 of m. Okay, so we mentioned that you can either use 100 as the mass, or you can use 1 as the mass, or you can use, let's say, you can even use pi as the mass, right? So any mass, it doesn't matter because finally they will cancel out here, right? So if you, again, use your calculator to check what the answer is. So the final answer is 0.0076, which is 0.76%. Okay, so this is how we calculate the percentage of the solvent in the dried fabric, right? So basically, it's using the mass conservation that the fabric mass is not going to change, right, during this dry process, while the solvent mass reduced, mainly because we're drying the fabric, right? And then secondly, it wants us to calculate the concentration of the solvent in the dryer exhaust in milligram per meter cube, right? And also give us the condition of the environment, which is at certain temperature and certain pressure, okay? So if you check what this problem asks us about, it asks about a mass concentration of the solvent in the air, right? Basically, it's asking us about the MA over V. That's why it's having the unit of milligram per meter cube, okay? So it may be quite difficult to directly get this quantity here, but we have introduced that these things can convert from one another, right? So what about NA divided by N? So NA here is basically the moles of the solvent in the air, and N here is the total number of moles of the air. So see what conditions we already have. So we have, basically, we know what is the mass of the solvent in the dried fabric, right? So we know that the solvent in the air will just be 97% of the original solvent amount, right? So that will be 97% multiplied by 0.45 m, because we only have 3% of the original solvent mass in the fabric. So 97% of the solvent will be in the wet air, right? So we know what is the mass of these solvent in the wet air. If we know the mass, we can just divide that by the molecular weight of A to calculate what is the number, or what is the moles of A, right? So what about the total number of moles for the gas, right? So we know that N, the total number of moles, will be equal to Na plus N of the air, right? So Na, we can already solve that because we know the mass of the solvent. We can divide that by the molecular weight to get Na. And for the N air, we also know the air, we also know the mass of air that's entering the system, right? We already know that for each pound of the solvent, so for each pound of the dried fabric, we have 8 pounds of the air, right? So based on the mass of the air, we can calculate how many moles of the air molecules are there, right? So this, because of that, we can solve for this problem, right? So MA, we already know that is 0.97 multiplied by 0.45. M divided by the molecular weight. So molecular weight is already gave us is 60, right? So 60 multiplied by 10 to the negative 3, right? Because we still need to use the standard unit, which is kilogram per meter cube. So this is number. This is the moles of the solvent. And in terms of the moles of the air, we have 0.55 multiplied by 8 of m. And then we'll divide that by the molecular weight of the air, which is 29 multiplied by negative 3, also kilogram per mole, right? So with this quantity here, we should be able to calculate what is the total moles of the species in this wet air here, right? And we already know what is the Na, right? The Na is just this. It's just this first term here, right? So basically, we can plug in these values, and again, these m will get canceled out. We can find out that the Na divided by n is actually 0.0458. Okay, so this is a mole fraction of the solvent in the wet air. So once we know the mole fraction, we can use this unit conversion again, right? So we can convert the mole fraction into the mass concentration. So the way we do that is basically Ma divided by V is equal to Na divided by N multiplied by P molecular weight of A divided by RT. So we have 0.0458 multiplied by the pressure multiplied by temperature. So I did notice multiplied by the molecular weight divided by 8.314 and multiplied by temperature. So I did notice that some of you actually directly use the Fahrenheit here. So we should use standard units, and the standard units for temperature is Kelvin, right? So you can first convert this Fahrenheit into Celsius, and this is actually 71.1 Celsius, right? So here, when we plug in the temperature, that will be 71.1 plus 273.15. Okay, so this is the actual temperature. And if you plug in this term, all of these together, you'll find out that the final answer will be 0.097 kilogram per meter cube. Okay, so the question asks us about the milligrams. So we need to convert the kilogram into milligrams. So first, we can convert that into grams per meter cube, right? A milligram, we just need to multiply that by 1,000. So 97,000 milligram per meter cube. Okay, so this is the final answer. The problem might look quite complex here, but if you just notice what is the unit we're talking about, and then convert that unit into some value that is easier to solve, then you should be able to calculate the correct answer. Okay, so I hope that this process is clear enough. I think maybe some of you used a different method here. So here I'm just trying to relate this question into the unit conversion, so it's easier to understand. Okay. So I think for this class, we just demonstrated two questions, and this is related to the unit conversion. So next class, we'll go through the review contents for the PM, and then we'll also go through some common problems or common questions you have in your homework. Okay, just feel free to let me know if you have any questions. I hope that you can understand how we're doing these, how we're working these problems out. All right.
Can you scroll down to the answer again, please?
Sure.
Thank you.
Yeah. Any other questions? Anything not clear? All right, if no more questions, I'll stay online for some longer time for you to copy the notes here. And if you don't have any other questions, feel free to leave. Okay.
Hi, Dr. Wang.
Yep.
So for the exams, are we going to have any question that will require us to print out the question paper?
I don't think so.
Okay, no problem. So something like the, so for example, if we have the log normal graph, we will have to print it out and draw the curves on the graph. So if there was something like that, then I could make arrangements for printing the question and something like that.
Yeah, so for those questions, I was thinking you can use your previous homework sheets. So if you still have them.
Okay.
Yeah, so that's a good point. I'll probably, I'll send a notification on Canvas.
All right, thanks.
Or you guys can, I'll just send you a clean piece of paper that has this semi-log plot. So you can use that in your exam.
Okay, thanks.
Okay. All right, if no more questions, I'll stop sharing the screen. And then let's meet again on Friday.